The night is quiet now, the kind of quiet that hums softly against the window. Your breath slows. Somewhere far beyond this darkness, stars are breathing too, though some have begun to rest. Imagine a sun that once burned bright, now folding into itself, its light tucked away under layers of time. That is where black dwarfs wait, not gone, not forgotten, just asleep in the deep velvet of the cosmos. They are the echoes of brilliance, cooled to silence, holding stories older than language. We'll drift there tonight, gently, to wonder what they are and why the universe calls them black. If this calm curiosity feels right to you, a quiet follow would mean more than you know, just a whisper of presence. Now, let the weight in your shoulders melt. The room is still. Close your eyes, and together we'll begin, slow and warm. The last glimmer will not come from a proud young sun or a crowded galaxy singing with newborn light. It will rise from a place so far ahead that our calendars fall silent, where the universe has slowed to a hush and almost everything that could happen has already happened. Not a blaze from living fire, not the crackle of a quasar's furnace, but a whisper from a star that forgot how to shine a very long time ago, so old and so cold that our warm sun would seem like a candle just lit beside it. We live near the beginning, even if it does not feel that way. The cosmos wears an age of about 13.8 billion years, a number that sounds like forever, and yet is only the first breath in a story that stretches past imagination. The path ahead runs through expanses so long that words wobble, time scales that break the rulers in our minds. On that path, stars go out one by one, galaxies thin and drift and darken. Even atoms, the sturdy seeds of matter, may loosen their grip. And still, after all that quiet, the universe saves one last surprise, the final light. Black dwarfs are not here yet. They cannot be. The universe is still too young to have cooled a white dwarf all the way down into blackness. But one day so distant that you would need a line of digits stretching across a room to write it, every star like our sun will finish its bright work and settle into that deeper sleep. A sky, once crowded with color, will be populated by these unlit pearls, the forgotten cores of a brilliant past. And then, after waiting longer than the cosmos has lived so far, repeated more times than a mind can comfortably hold, a few of those cold remnants will remember how to fall apart. They will not be ordinary supernovas. Their fuel will be the rules of the very small, still at work in the vast darkness. They will flare. They will be the last fireworks. For now, we drift in the Stelliferous era, the age of stars. It is the warm middle of the grand night, when hydrogen kindles in countless cores, and light and heat pour outward, building the heavy notes on the periodic scale that let planets harden and oceans form and living chemistry wake. This age feels endless from our roof under the sky, and yet on cosmic clocks, it is a quick, brilliant interval, already sliding toward dusk. To find the thread that ties our present to that far, cool future, we sit with the life of ordinary stars like our own and follow them gently toward their rest. Our sun has kept a steady fire for about 4.6 billion years already, a full third of the life it can expect. In its quiet heart, simple hydrogen is gently stitched into helium. That stitching releases energy, and that energy comes to us as daylight, the softness of morning on leaves, the warmth that makes weather and seasons and the breath of mammals possible. The craft is astonishingly efficient. Each second, roughly 600 million tons of hydrogen become helium, and about 4 million tons of mass simply melts into pure energy. As if the sun sighs and light comes out. With this careful pace, it can keep up its bright work for about 5 billion more years before the balance changes. As the core runs low, it tightens like a cooling fist and grows hotter, the outer layers feeling that change swell and loosen. The sun billows into a red giant. Its skin expands until Mercury and Venus are likely swallowed whole, and even Earth sits in a dangerous, blistering breath that may sweep it away. In that time, the outer layers are barely held. Winds lift them, silk by silk, and send them flowing outward to make a thin, glowing shell, a planetary nebula, a lantern blown from starlight itself expanding and fading into space. Left behind is the core. It can no longer keep up the fusion that once paid all the bills. What remains is compact and intense, the heart without the halo, an object we call a white dwarf. Picture something about the size of Earth, yet holding close to 60% of the sun's original mass. If you prefer a smaller image, a school bus pressed into a sugar cube, a teaspoon of this matter weighing around 15 tons in our familiar gravity. This is density as an experience. Gravity so near you can almost feel its pull in your teeth. A white dwarf does not burn. It glows because it is still hot from the violence of its making, the way a coal shines long after the flames are gone. Fresh from birth, a white dwarf's surface can soar above 100,000 degrees Celsius, blue-white, dazzling in a telescope. Then it begins to cool, patiently, for times longer than civilizations can imagine. The question is, why it does not collapse while it cools? The answer belongs to the small, quiet rules of quantum life. Inside, the matter is squeezed so fiercely that the usual give of gas no longer holds the weight. Instead, what props the star up is the etiquette of electrons, a rule that says two of them cannot sit in exactly the same state at once. You can imagine a crowded theater where every seat is already taken. Latecomers are forced higher and higher into the balcony, making a pressure that has nothing to do with heat, only with the refusal of identical particles to share a chair. This no sharing the same seat rule builds an invisible scaffolding. Even if the star cooled to the coldest temperature nature permits, that quantum scaffolding would still brace it against collapse. And so, a white dwarf endures, not by burning, but by being too crowded to fall any further inward. There are so many of these embers. In a large galaxy, they probably number in the hundreds of billions. Any star that starts life with a mass somewhere between about 1/2 and 8 times that of our sun will finish as a white dwarf. Heavier stars live fast and die loud, exploding as supernovas and leaving behind neutron stars or black holes. Very small stars sip their fuel so slowly that none has had time to reach the end yet, while the universe is this young. The broad middle, the stars you'd see if you could count without blinking, are the ones that make white dwarfs. They are the majority of stellar goodbyes. We have met thousands already. They glow softly in catalogs and through instruments, small diamonds in the dark. The nearest is not distant at all by cosmic measure, Sirius B, a faint companion circling the bright star. Sirius A, only about 8.6 light-years from our doorstep. It takes roughly 50 years to go once around its partner. and though it carries a mass similar to the Sun's, it looks about 25,000 times fainter than Sirius A. The contrast, a reminder of just how tiny and dense white dwarfs are compared to ordinary stars. If you could somehow stand on the surface of Sirius B, which you could not, the gravity would multiply your weight by something like 4 million. Bones, muscles, metal would flatten into a film of compressed atoms. It is a place where everyday words fail, and the imagination must slow down to keep its footing. Yet, in other ways, white dwarfs are varied and expressive. Some wear thin atmospheres of hydrogen and appear as the Da family. Others show helium or trace elements, and their temperatures range from feverish to merely warm, depending on how long they have been cooling. Each one is a different note in a long, fading song. Over the ages, the physics inside these stars continues its quiet work. As white dwarfs cool, their interiors can crystallize, turning into vast cosmic diamonds, orderly lattices of carbon and oxygen frozen by time and pressure. That image is romantic, yes, but it is also true in a simple way. The core becomes more solid, more still, the way a lake hardens in winter. Only this winter lasts longer than languages last. In that unhurried deep freeze, the glow dwindles through colors: bluish white to white, white to amber, amber to a deep cherry, then to red embers, then to a heat too faint for human eyes. When enough ages have passed, so many that counting feels like poetry more than arithmetic, those black dwarfs will fill the quiet. And here the universe hides its last trick. Even with almost no heat left, the packing of particles inside these corpses never stops following quantum rules. In the densest hearts, slow reactions can still creep forward, nudging lighter elements toward iron, the end-of-the-road metal for stellar alchemy. When the core's balance tips, when iron wins and pressure can no longer help, there is nothing left to cushion the inward rush. A failure of support becomes an avalanche. The old star, cold and dark and convinced of its stillness, tears itself open in one last bright contradiction. The flash is not youthful fire, but the last proof that the laws of the small keep working even when the universe has nearly run out of energy. Between our warm present and that final spark lies a patient procession. Star by star, the markets of light will close. Galaxies will lose their bright neighborhoods and become more like thin settlements, then ghost towns. Gravity will gather what it can. Stray worlds will wander. Cold collisions and soft captures will play their slow games. And still, the little white cores go on cooling, some crystallizing, some merging and flaring briefly, many simply continuing their long descent toward quiet. The story asks for patience and gives it back as wonder. Here at the bright beginning of the tale, we're still under a steady sun, counting nearby embers like mileposts. Sirius B circling every 50 years, Procyon B keeping watch, 40 Eridani B noted long ago. The figures steady our sense of scale. They don't shout, they orient. And with that footing, the path narrows from the grand sweep to a closer look at a single remnant, how its surface speaks, how its quiet layers remember the star it once was. Up close, some of these compact embers wear a thin helium skin. Astronomers call them DB white dwarfs. Others carry faint signatures of carbon, oxygen, even trace metals, small colors that hint at their past and the chemistry that once simmered within. Those surface clues are light but telling, and beneath them, the real transformation proceeds. Slow and exacting, turning a stellar core into a planet-sized crystal, the largest diamond the universe will likely ever make. When a white dwarf is newly born, its interior is a hot, dense ocean, a plasma of carbon and oxygen nuclei, moving through a sea of degenerate electrons, all pressed tightly together by gravity's insistence. The nuclei wander and jostle, vibrating and colliding in the furnace heat left over from a star's last breath of fusion. Time passes in wide pages. As the white dwarf cools over billions of years, motion softens. The thermal buzz grows quieter, but the gentle electric attractions between those positively charged nuclei do not grow quiet. They remain steady, patient, unblinking. Eventually, the balance tips. The pull between neighbors becomes stronger than their restless shuffle, and the particles begin to settle into places that fit. From the very center, where the cold arrives first, the white dwarf starts to crystallize, not as a metaphor, but as a physical truth. The carbon and oxygen arrange themselves into an ordered lattice, each nucleus sliding almost reluctantly into a fixed relationship with its neighbors. The pattern is the same geometry that makes diamond on Earth, a face-centered cubic lattice, a tidy architecture where each carbon sits in a tetrahedral embrace with 4 partners. It is simply that the stage is larger, not a ring setting, not a gemstone in a palm, but a crystal the size of a planet. Think of the scales the way one might compare a raindrop to an ocean. A diamond you might hold here on Earth could gather on the order of 10, 22 carbon atoms already uncountable to a mind that knows chairs and trees. But a fully crystallized white dwarf can bind something like 56 carbon atoms into one vast cohering structure, a single planetary diamond lit from within by its own leftover heat. We would not know this without delicate evidence, but the universe left a clue, and we learned how to listen. In 2019, astronomers working with the Gaia Space Telescope noticed a curious pause in the cooling of many white dwarfs. Gaia measures brightness and color with exquisite care, and in those measurements sat a population of stars that were brighter than their temperatures should have allowed. The extra light, it seems, came from the latent heat of freezing energy released when the interior shifted from liquid to crystal, just as water offers up warmth as it turns to ice. The stars were, in their unhurried way, giving off the heat of formation a second time, and that glow slowed their fade. It was the universe's way of confirming that a diamond was growing in the dark. This solidifying does not happen in a rush, and it does not happen everywhere at once. The white dwarf cools from the core outward, and the crystallization front moves with it, a slowly expanding shell marking where order has replaced the old fluid dance. It can take hundreds of millions of years for this frontier to pass from the center to the surface, an entire epoch where the star's interior holds a layered complexity. At the heart, a solid crystal. Above it, liquid plasma, still sloshing lazily. Between them, a borderland where tiny crystals appear, dissolve, and reappear. A phase change ongoing like winter advancing and retreating across a quiet lake. Eventually, given time, the solid wins, and the whole star becomes a rigid jewel, a crystalline core wrapped in thin shells of lighter stuff, and topped by a faint atmosphere of hydrogen or helium. Once in this state, the star is as dense and settled as a white dwarf can be, without crossing a boundary into something altogether different. There, it will remain for a very long time. How long depends on how we hold the phrase very long. in our mouths. Cooling takes patience because a white dwarf is small in surface but deep in stored heat. The rate at which it loses energy depends not only on temperature but on the skin it has to radiate through, and that skin is tiny compared to the broad face of a normal star. The Stefan Boltzmann law, which ties a body's brightness to its heat and its area, quietly governs this fade. With temperatures of thousands or tens of thousands of degrees but a surface area roughly a millionth that of the sun, a white dwarf leaks its hoarded warmth very slowly. It is like a kettle the size of a mountain trying to cool through a teacup's rim. Across the Milky Way, some of the oldest white dwarfs we know are about 11 billion years old, nearly as ancient as the galaxy itself. They have fallen from newborn surface temperatures above 100,000 degrees Celsius to around 3,000 degrees Celsius. In visible light, they read as a deep red ember, difficult to see even through generous telescopes, yet still glowing, still sending out the last of the heat from their creation billions of years ago. And they will keep glowing for trillions of years more. The numbers drift toward the astronomical, and then beyond it, to the poetic. The coolest white dwarfs detectable today sit around 2,500 degrees Celsius, shining mainly in the deep infrared. To cool from 100,000 degrees Celsius to 2,500 degrees Celsius takes roughly 10 billion years. But to slip the rest of the way down to just a handful of degrees above absolute zero demands patience on an altogether different scale. About 10 quadrillion years, a 1 followed by 16 zeros, a million billion years. For perspective, the universe itself has only existed for about 13.8 billion years. White dwarfs will continue their slow exhale for a million times longer than that. Over this vast itinerary, their colors change like the sky of a very long twilight, blue-white to white, white to yellow, yellow to red, red to a color the human eye cannot see. The first few billion years go by in relatively quick steps. Then, as the star dims into the infrared, the cooling crawls. Tens of billions of years to move from red to infrared. Hundreds of billions to go from bright infrared to dim. It is the asymptote of winter. Around the mark of 100 trillion years, a typical white dwarf can grow so cool and faint that it no longer offers any detectable radiation to our best instruments. Its light hidden below the threshold of noticing. Its surface temperature rides close to the gentle hum of the cosmic microwave background, that faint afterglow of the Big Bang that still fills every direction. When the star's warmth matches the room temperature of the universe itself, the distinction between ember and night becomes hard to draw. At that stage, it is no longer a white dwarf in any practical sense, but something we speak of only in theory and anticipation, a black dwarf. The name can mislead. These are not black holes. They do not swallow light or bend space into a cave. They are black in the simple way that a thing becomes black when it no longer emits a glow we can catch, when it offers almost no light at all. They are the ultimate stellar remains, cold, dark, and patient beyond any experience, the end state of stars whose heat has been all but given back to the void. None exist yet. The universe is not old enough. Even the very first white dwarfs, born from the earliest stars more than 13 billion years ago, are still warm enough to whisper in the infrared. They will keep whispering for trillions more years before that whisper fades into the background hush. The first true black dwarf will not arrive for at least 10 quadrillion years, perhaps longer. depending on the subtleties of cooling and on how strictly we define black. Hold the timeline gently. The universe today, 13.8 billion years old, is still in its morning. Our sun, which will become a white dwarf in about 7 billion years, will then begin its own long fade, cooling for something like those same 10 quadrillion years before it becomes a black dwarf. That is about 700,000 times longer than the universe has lived so far. If you compress the age of the cosmos up to now into a single second, the time needed for the sun's remnant to reach black dwarf stillness would stretch to about 8 days. Imagine measuring with meters. If the present age were just 1 meter, the cooling distance would be 700 kilometers. If the age so far were 1 hour on a clock, the cooling would ask for around 80 years. However we scale the picture, the feeling does not change. This is a patience so large, it becomes a kind of quiet wonder. Inside these cinders, the structure settles, even as time swells. A crystalline core holds most of the weight, carbon and oxygen in that face-centered lattice, wrapped by thin layers of lighter elements and then by an atmosphere made spare from hydrogen or helium. The whole object sits close to the maximum density a white dwarf can keep without collapsing into some other fate. It will not sink further, because electron degeneracy still props it up, independent of heat. Even at the cold limit, the electrons keep their polite distance in quantum seats. No two can share. Cooling spreads outward from the center, and the boundary between solid and liquid is like a line of frost creeping along a window, a frontier that moves, pauses, then moves again over hundreds of millions of years until the last liquid pockets freeze and the star is a planet-sized gemstone, alone but enduring. All the while, its tiny surface area keeps the leak of energy modest, as if the star were wrapped in a thick coat. The Stefan Boltzmann law need not be recited like a formula to feel its meaning. Small radiators cool slowly. What warmth remains drains away along a curve that flattens and flattens. It is easy to imagine the colors. First the bright steel of a weld, then the honey of a bulb turned low, then the claret of coals, then a heat that exists for instruments only, like a heartbeat beneath quilts. We sometimes give these different outfits names. D, when a thin hydrogen veil is on top. DB, when helium leads the show. Some spectra confess a dusting of carbon or oxygen or metals, reminders of the layers that rose and fell inside the star before this quiet. These labels are not meant to distance us. They are simply ways to notice who is wearing which coat on a cold night. The coats change slowly, too, as gravity and subtle convection pull elements upward or push them down, blending and sorting in a choreography that continues even when fusion is gone. Gaia's discovery of the latent heat plateau told us the timing of the freeze, but it also gave us a feeling for how the process keeps the star brighter a little longer than expected. A phase change is a gift of energy. It must be paid out, and the star pays it softly. That is why some white dwarfs, with the same color as others, shine a little more. They are in the act of becoming solid, and the act itself gives off light. Imagine a pond at dusk throwing a final shimmer as it catches ice. Now stretch that scene over hundreds of millions of years, and a globe as large as Earth. Beyond even that long season, the arithmetic of cooling carries us into the far reaches of time. The list of intervals sounds like a poem of winters. Tens of billions of years to cross into the infrared, hundreds of billions to dim further, around 100 trillion years to become effectively invisible by any practical telescope surface heat, approaching the cosmic microwave background. And then the longer march, 10 quadrillion years to settle within a few degrees of absolute zero, to become a black dwarf in the strictest sense of the word. Numbers do not ask for belief. They simply anchor the imagination, which might otherwise float away. We can keep the scale close. The universe so far, 13.8 billion years, shrinks, in our pocket metaphor, to 1 second, or 1 meter, or 1 hour. Against that, a typical white dwarf's cooling runs about 8 days, or 700 kilometers, or 80 years. Our sun follows a similar path. Roughly 7 billion years from now, it becomes a white dwarf, then spends about 10 quadrillion years, 10 quadrillion cooling, toward black dwarf stillness. And even in that seeming silence, there's structure, crystals forming, latent heat released, atmospheres sorting, spectra whispering history. The same laws, electromagnetism, quantum rules for electrons, the measured flow of radiation keep working, only softer. A white dwarf doesn't give up to become a black dwarf. It completes an unusually long sentence. When the light finally slips below any chance of finding, the laws that shaped it remain, steady as ever. Set beside those spans, black dwarfs live in a future where calendars blur. On any human measure, a year, a lifetime, a lineage, they sit at a distance that feels like forever. While those embers cool into hush, the wider scene changes too. Ordinary stars finish their work. Even the careful red dwarfs, the frugal suns that burn for trillions of years, run out. Thrift is not immortality. By the time the first true black dwarf exists, the last red dwarf will have faded billions of years earlier. The age of starlight, the stelliferous era, will have folded its tents, and the stage will belong to remnants. The homes of stars will not look familiar either. Galaxies are lively today, with spirals and bars and bright knots of birth, but they are also communities bound by gravity's bookkeeping. Over enormous spans, stars trade tiny bits of energy through close passes. Some bleed momentum in tight dances and give it away in long ones. Gravitational waves carry off thread-like losses from rare, compact encounters. Trillions upon trillions of years smooth these books. Some stars drift inward and are swallowed by the central black hole. Others get a kick and are flung out, solitary travelers into intergalactic dark. Clusters that now gather galaxies like villages will loosen and wash apart. The neat architecture we sketch in atlases, galaxies in clusters, clusters in superclusters dissolves until most things are simply alone. Planets do not keep their addresses. Earth will be gone when the sun swells into a red giant. Farther out, survivors will not necessarily stay moored. Slow gravitational tugs rearrange orbits over ages, and wandering stars can tease a planet loose. Many worlds will spiral inward and vanish into the cooling embers of their parent stars. Many will be thrown into the black between systems. What we now call a solar system becomes a memory, a single cooling remnant gliding through space, perhaps with a loose retinue of debris and darkness, perhaps with nothing at all. The background of the universe itself grows more silent. Today, the cosmic microwave background bathes everything at about 2.7 Kelvin, a faint relic glow from the Big Bang. Expansion stretches that light into longer and longer waves. In something like 10 quadrillion years, the background will sink to less than a millionth of a degree above absolute zero. The cosmos becomes a deep freeze in practice. Temperatures everywhere, pressed close to the coldest nature allows. Energy spread too thin to rouse anything easily. No stars shine. because no stars remain. Galaxies are memories, planets are rumors, distances are enormous, and time feels like an ocean without wind. This can sound like an ending without movement, a final page pressed flat, but stillness is not the same as nothing, and the rules that shape the bright universe do not retire. Quantum mechanics does not care whether the stage is young and loud or old and quiet. The laws remain. It is within these laws that the last surprises find room. Holding the clocks up to the light helps. Cosmologists speak of wide eras, each given its name by the processes that dominated. We live in the Stelliferous one, which began roughly 100 million years after the Big Bang, when the first stars flared into being, and which lasts until the last stars die. The sunset of this era arrives around 100 trillion years. From the start 10, 14 years, 100,000 billion. Even the humblest red dwarfs will have emptied their small cores by then, cooling into white dwarfs. Natural fusion for all practical purposes goes dark. Aside from rare, exceptional sparks will come too gently. After the stelliferous age softens away, the degenerate era takes the stage, named not for decay in the common sense, but for the quantum degeneracy that props up matter inside white dwarfs and cousin remnants. This long interval runs from about 10, 14 years to around 10, 40 years. The cast is sparse but weighty: white dwarfs, neutron stars, and black holes. None of them makes new energy the way stars did. They simply own leftover heat and slowly let it go. Early on, white dwarfs cool into black dwarfs, their light crossing thresholds until instruments could not notice it anymore. The exact schedule depends on mass, mix of elements, and the fine points of how heat leaks out, which is why estimates for a typical white dwarf to become a black dwarf span an almost comical range, roughly 10, 15 to 10, 30 years. That spread, 15 orders of magnitude, reminds us how far beyond observation we travel here and how carefully we must hold our certainty. Yet even the longest of those cooling times will seem like a preface compared to what waits deeper in the calendar. Around 1036 years, another question enters the room. Do protons, the sturdy bricks of atomic nuclei, last forever? We do not know. Some theories suggest they might eventually decay into lighter things, like positrons and photons. If that is true, then matter itself is not permanent on the longest scales. Experiments have only told us that if protons decay, their lifetimes exceed about 1034 years. Many models place the act, if it happens at all, somewhere between 1036 and 1045 years. Take those as signposts, not certainties. If they are right, black dwarfs would ever so slowly lose the very particles from which they are built, evaporating in a different sense, grain by grain. If protons are stable past 1040 years or forever, then those dark stars persist into later chapters of time. Beyond this, the universe is ruled by the massive and the quiet. The black hole era follows, when the only meaningful energy trickles out of horizons. In 1974, Stephen Hawking pointed out that quantum fields near a black hole's edge can produce pairs of particles. One falls in, the other escapes, and the hole's mass shrinks by the tiniest measure. The rule of thumb is simple. Small black holes fade relatively quickly, Large ones hold on almost unbelievably long. A hole with the mass of the sun would need around 1067 years to evaporate fully. The giants at galactic centers, with millions or billions of solar masses, take times at or beyond 100 years. Against these spans, the formation of black dwarfs looks like an eye blink, the way a century looks next to a mountain's age. When even the great black holes have sighed away into particles and faint radiation, what remains is the so-called dark era. Picture a cosmos filled with cold black dwarfs, if protons endure, or with the sparsest sea of particles and faded photons if they do not. Temperatures are pressed against absolute zero. Distances are unhelpful. The density of matter is so low that encounters are rare to the point of myth. No engine remains to do work in the ordinary sense, no gradients steep enough to turn, no warm pockets to stir. This is the heat death. Energy spread out as thin as it can be, entropy near its ceiling, the clock not broken but wound all the way down. And yet even here, nothing is not quite the right word. The fact that structure no longer changes in ways that please our storytelling does not mean the laws stop humming. Quantum fields still fluctuate. Particles still obey their statistics. If protons are stable, black dwarfs persist as the quiet furniture of this chill, and within the densest of them, the miniature arithmetic that nudges elements toward iron can continue. Where that slow nudge reaches a tipping point, something dramatic can still happen. The last supernovas, born not of hot fusion, but of the failure of quantum support in a star that is cold in every way we usually mean. These are the iron supernovas of the far future, one more proof that the universe always keeps a few embers in reserve. Everything about these spans of time resists easy grasp. Numbers turn to weather rather than facts, but comparisons can lend a hand. The time for white dwarfs to become black dwarfs, those 10, 15 to 10, 30 years, is longer than the universe's current 13.8 billion years, by factors ranging from 100,000 to 1 trillion. If we compress all that has happened so far into a single second, then the interval before black dwarfs appear stretches to somewhere between about 3 years and 30 billion years, depending on which cooling estimate you favor. If the age so far were a single meter laid on the floor, the white dwarf to black dwarf cooling would run about 700 kilometers. If the age so far were 1 quiet hour, the wait to blackness would be something like 80 years. Scaling does not change reality. It only makes room for our imagination to sit down. Meanwhile, around those cooling embers, the rest of the story keeps thinning. Red dwarfs end their long twilight and fade. The last natural thermonuclear fires go out. Galaxies, starved and tired, shed their citizens to the central pit or to the edges of nothing. A few binary remnants may still dance, merging after unimaginable times and flaring briefly, but those are flickers on a canvas that grows more sparse. The cosmic microwave background, once a 2.7K whisper, loses pitch until it is practically silence. Planets do not persist. Either they fell inward long ago, or they wander as airless stones, warmed by nothing, shepherded by no sun. It feels right, in this quiet, to remember the gentler pieces of the physics that carry through. Degenerate matter is simply the consequence of electrons refusing to sit in the same quantum seat. That refusal holds up white dwarfs, no matter their temperature. The slower cooling is partly because those stars are small in surface but immense in stored heat. The Stefan Boltzmann law tells us that radiating away energy depends on both temperature and skin. And a white dwarf has little skin to share with space. None of this is a lesson to memorize. It is a way of sensing that the same rules that made galaxies and rain now make a very long winter. If protons do decay, the late degenerate era becomes a gradual unwinding of matter itself. Black dwarfs thin, neutron stars quietly shed. Even iron, usually the destination, is not immune. It becomes a waypoint. If protons do not decay, the black hole era takes its bow, and the physics at horizons writes the last ledger entries, grain by grain, through Hawking evaporation. In either path, the dark era arrives eventually, and with it, a steady background where change is rare and fine. Perhaps the most human thing in this landscape is that the story keeps a place for surprise, even as it narrows. Deep inside the coldest dwarfs, the slow bookkeeping of nuclei can tip the balance. When iron takes over and the invisible scaffolding of quantum pressure cannot quite carry the weight, collapse follows sudden after ages of calm. That failure becomes light again, a supernova in a universe that has forgotten how to expect it. These are the last fireworks, sent from a stage without an audience, proving that nothing left to happen is never entirely true. Hold the calendar one last time. The Stelliferous age closes near 10-14 years. The degenerate age drifts to 10-40. Black dwarfs first appear somewhere between 10-15 and 10-30, depending on birth and chemistry. If protons are mortal, their lifetimes likely exceed 10-34 years and may reach 10-45. A solar mass black hole needs to 10-67 years to fade. The giant engines at galactic centers to 10-100. In 10 quadrillion years, the background glow cools to less than a millionth of a Kelvin above absolute zero. These figures don't ask to be adored, only to anchor the feeling that the universe is wide enough for both blaze and hush. In that wide, cold, black dwarfs wait, crystallized hearts of former suns. Within a few, the seed of one last brightness remains rare, late, brief, but real. After even those flashes pass, the quiet is not sorrow so much as completion, like snow that has fallen all night and now lies without a mark. And if we press the scale further, the distances turn wordless. A proton lifetime near 1036 years is roughly 10 trillion times the universe's current age. If all we've lived so far were 1 second, that hypothetical decay would sit 300 trillion years away, about 20,000 times longer than everything to date. Beyond that, the largest black holes endure to 10-100 years, a googol, a 1 with 100 zeros longer than now, by to 10-90. Metaphor gives up before those spans. They are simply vastnesses you don't walk with comparisons, only accept with a slow breath. What matters for our path is gentler. Black dwarfs arrive early on that grand calendar. Early not in any human sense, but early compared to those oceanic spans of black hole fading. By the time the universe is around 10-30 years old, and certainly by 10-40, most white dwarfs will have cooled into darkness, assuming protons endure. These will be the common furniture of existence, countless trillions of planet-sized crystals adrift, stretched so far apart by expansion and chance that most will never meet another companion again. Their skins will rest less than a single degree above absolute zero, They won't glow in visible light, or in infrared, or in any band a camera could hope to touch. Each one will be a memory so thoroughly cooled that even the afterheat of dying has long since been poured into the night. And still, the interior will not be perfectly idle. Deep within those diamond hearts, a quiet arithmetic goes on, tiny, improbable transactions that, given enough ages, add up to a consequence. The doorway to that arithmetic is quantum tunneling, one of physics' softest but strangest permissions. Classical thinking insists that to cross a barrier, you must climb it or break it. A ball without enough speed to crest a hill rolls back down, always. Quantum thinking says the ball is also a wave, spread out in possibility. Part of that wave seeps into the forbidden ground beyond the hill. Most of it reflects, yes, but not all. A small, non-zero chance remains that the particle turns up on the far side without ever cresting the top. Everyday life hides this effect, but it is everywhere once you look. Radioactive nuclei shed particles because those particles tunnel through the nuclear wall. The scanning tunneling microscope reads surfaces by coaxing electrons to tunnel across a whisper-thin gap. Even the sun benefits. Its core is about 15 million degrees Celsius, a temperature classical calculations once judged too low for hydrogen to fuse efficiently. Quantum tunneling narrows the last portion of the barrier so that fusion proceeds anyway, and so day breaks on Earth. Black dwarfs are the opposite of a fusion furnace. Their interiors live a breath above absolute zero. Nuclei are fixed at the nodes of a crystalline lattice, a carbon-oxygen diamond bound by pressure and order. They shiver a little, as everything does, but they do not crash together with the wild energy of a star's youth. The electromagnetic repulsion between their positive charges builds a tall, thick wall. Classically, no fusion should occur. No amount of waiting should change that picture. Quantum mechanics keeps a door ajar. The wave functions of those nuclei extend into the barrier and beyond it. The probability of tunneling is absurdly tiny, a number so fragile it might seem like zero in any practical age. Raise the barrier's height or widen it, and the chance falls exponentially. But time is a lever. Given more of it than words can hold, even the rarest dice eventually land as they may. The far future offers that time in abundance. A pair of physicists, Fred Adams and Gregory Laughlin, ran their fingers along this logic and did the careful sums. They followed the tunneling steps available in a chilled lattice of carbon and oxygen and asked how the composition would drift as the ages compounded. The answer glides in on a whisper, slowly, with intervals measured not in billions or trillions of years, but in spans that make even those seem brisk. Over about 1,500 years. Yes, a 1 with 1,500 zeros. The black dwarf's heart can gradually reforge itself. Carbon finds partners and becomes heavier. Oxygen does the same. Neon appears, then magnesium, then silicon, each step a tiny triumph of tunneling through a barrier no heat could soften. The energy those reactions release is not enough to warm the star. It bleeds away at once into the near absolute chill. The temperature remains pinned to the background, black and still. Only the ledger of nuclei changes, atom by atom, step by slow step. It helps to picture the lattice as a quiet city at night. Most windows are dark. Here and there, very rarely, a light blinks on that is a tunneling event, and two residents slip into a new apartment together, their lease rewritten. The building doesn't grow warmer, The hallway stays cold, but over a span so long you cannot count the seasons, the tenants become, on average, heavier, more tightly bound. The city's character changes even as its street lamps stay unlit. Why these particular elements? Because of a deep preference in the nucleus. Lighter atoms, when fused up to a point, release energy and settle into more stable arrangements. Neon, magnesium, silicon, each lies further along that gentle downhill in the binding energy landscape. The tunneling steps must be done in many moves. Each barrier is high and wide by everyday standards, and the odds of success are thinner than air. But with a calendar as broad as 1,500 years, patience becomes a power in itself. One improbable event becomes a sequence becomes a chain. Eventually, the chain nears a quiet shore. Iron gathers like silt at the mouth of a river. In nuclear physics, iron and its neighbors sit at the bottom of the energy well. You can release energy by moving toward them from either side, but you cannot go further down by pushing past them. Fusing iron into heavier elements costs energy rather than pays it. This is the point that halts ordinary stars. They can make iron cores, but they cannot profit by fusing iron into anything heavier. So pressure support collapses, and a different drama begins. In our frozen dwarfs, iron does not arrive in a blaze. It sedimentates through eons of tunneling, arrives as a conclusion, not as an event. Through all of this, the outside world stays nearly featureless. Expansion continues its steady stretch. The cosmic microwave background, once 2.7 Kelvin, drifts toward numbers that feel like poetry. Millionths of a degree above absolute zero in 10 quadrillion years, and lower still after that. If protons are unstable, then somewhere between 1036 and 1045 years, the bricks of nuclei begin to crumble, and black dwarfs lose substance grain by grain. If protons last beyond 1040 years or forever, then the dwarfs keep their mass and their slow alchemy. Either way, the galaxies we knew have long since washed apart. The last red dwarfs have gone quiet. The map is mostly empty, with lonely markers far between. Inside a single black dwarf, the lattice keeps its poise. Electrons remain in their quantum seats, refusing overlap, holding gravity at bay without any help from heat. The crystal remains so stiff that pressure waves would cross it like sound through diamond, and yet the nuclear composition keeps leaning toward iron, click by almost non-existent click. Nothing in the room changes temperature. No color returns. There is only the arithmetic of the small operating on times the large can barely name. It is tempting to imagine that such changes cannot matter, but even in a universe of quiet, thresholds exist. As iron accumulates and lighter nuclei are spent, the star's ability to support itself on quantum etiquette alone can falter. The detailed pathway is delicate, set by mass, by the exact mix of elements, by the whisper-thin probabilities of each tunneling step, but the destination is not. Where the core's composition crosses the invisible line, a new instability grows. The lattice, perfect and cold, cannot find enough pressure from its electrons to counter gravity in that iron-rich heart. Collapse begins, not with a rise in heat, but with a failure in balance. The star, which has sat unchanged to any casual glance for ages past, number, tips. All of the timing that led to this is spread across comparisons meant only to give a handhold. A proton lifetime of 1036 years means in our 1-second universe, a weight of 300 trillion years. The evaporation of the grandest black holes at roughly 100 years is a span beyond analogy. Against those, the appearance of black dwarfs by 30 to 40 years is early dawn, and their temperatures fractions of a degree above absolute zero mean no glow will betray them. They are invisible by every instrument we could imagine building, because invisibility is their definition. The heat from their making, and even from their subtle phase changes, has long since been traded for the thin warmth of space. And yet the core writes its own chapter, letter by letter. Carbon finds carbon, oxygen finds oxygen, neon, magnesium, silicon accumulate through a chemistry of chance, permitted by quantum law. Iron gathers last, not because it is lively, but because it is the most restful configuration the nucleus knows. The whole process is a lullaby that recites itself over and over for a span so long that numbers fall asleep trying to count it. Roughly 1,500 years to do meaningful work, perhaps more for certain masses, perhaps less for others. It is the kind of sentence only the universe can finish. The great backdrop does not intervene. Galaxies do not return. The microwave background does not warm. Protons either quietly unravel on their own timetable, or they do not. Black holes dwindle by hawking radiation over calendars so extended that even the word calendar feels like a joke. Black dwarfs drift, separated by gulfs that expansion keeps widening. Very rarely, two remnants might pass close, trading a gravitational glance. More rarely still, they might merge. Most will not. Each is a solitary room with its own invisible clock. Somewhere along that long gradient of mass and composition, in one of those silent, unseen rooms of the cosmos, an iron-rich heart will finally cross its invisible line. Electron degeneracy, the strange quantum scaffolding that has held gravity at bay, will no longer be enough to shoulder the weight. Collapse will begin, racing inward at the fastest pace that rigid matter can permit. It won't be a warm awakening, but a contradiction made real. A supernova, born from a star as cold as the universe itself. An explosion not of fire, but of structure giving way. Against the endless dark, it will flare for a heartbeat rare, small, but utterly real. The last explosions will come from the coldest places. In that meeting of two kinds of patience, the slow cooling of time and the slower tunneling of quantum chance, the universe plays its last improbable move. Even after the script seems finished, it leaves one more gesture on the page. Black dwarfs, those invisible diamonds adrift between almost nothing and nothing, are not simply the end of stellar life. They are the quiet workshops where the final sparks are prepared, not by heat, not by pressure, but by probabilities so faint they could never be spoken, only waited for. And deep inside those waiting cores, the story flattens into iron. Once nuclei reach that element, the road downhill ends. To move further would cost energy instead of giving it, and no black dwarf has a furnace left to pay such a price. So the iron gathers slowly, steadily, flake by flake across spans that make every age before seem like a breath held in the dark. The center grows heavier. Quietly, almost shyly, a threshold approaches. There has always been a line that compact stars cannot cross without consequence. The Chandrasekhar limit, named for Subramanian Chandrasekhar, who traced its mathematics in 1930. About 1.4 times the mass of our sun, that is the neighborhood of the line. Below it, electron degeneracy pressure can shoulder gravity. Above it, that quantum scaffolding buckles. A white dwarf that creeps toward this boundary by sipping matter from a companion grows uneasy. As it nears the limit, support fails, heat flashes up, fusion runs away, and the star pulls itself apart in a thermonuclear blossom we call a type Ia supernova, briefly bright enough to outshine a galaxy, steady enough in peak light that astronomers use it as a yardstick across the deep. Now hold that picture in cold hands and remove the flame. Imagine a black dwarf whose interior made iron-rich, not by heat, but by eons of quantum tunneling, has drifted toward that same limit. No companion feeds it. No accretion disk glows. Only the slow arithmetic of nuclei, adding iron to iron, nudges the core toward critical mass. The electron pressure that once stood like a quiet, perfect wall begins to falter. Collapse starts, but without the sudden fever of a type Ia. It is a fall that begins cold. As density climbs, electrons are squeezed into higher and higher quantum seats. Their energies soar, not as heat felt at the surface, but as a deepening tension in the core. Then, a different door opens. Electrons combine with protons inside iron nuclei, making neutrons and releasing streams of neutrinos that slip away almost without interaction. This is electron capture neutronization, and it steals the very pressure that was holding the star up. In a heartbeat of physics, an Earth-sized object races inward toward a core only a few kilometers across. Gravitational potential energy floods the interior. Iron, stable in a calm, becomes fragile in a crush. Nuclei are shattered and rebuilt. Shock waves form in matter that had not felt a warm day in a trillion ages. The result is an explosion, not the bright blue-white shout of a type Ia lit by carbon-oxygen burning, but a quieter detonation born of an iron heart failing its support. A black dwarf supernova, sometimes called an iron supernova, because its fuel is the very stability of iron under extreme compression rather than fresh carbon or oxygen ready to run hot. The mechanism rhymes with a type Ia. A remnant crosses the Chandrasekhar limit and cannot hold. Yet the details are different. Colder onset, iron-heavy composition, and a budget of energy that is modest by supernova standards. Models suggest a light perhaps 100th to 1,000th of a normal type Ia. Fainter, yes, but set that against a universe gone dark for 10, 40 years or more, and even a whisper becomes a cathedral bell. For hours or days, a point will shine in an otherwise unlit cosmos. Photons will scatter outward across a space that has forgotten what sparkle means. Neutrinos will pass nearly unbothered through the emptiness. A tremor of gravitational waves will ripple the fabric that holds everything. Then the light will ease, the ash will drift and cool, and the darkness will reknit itself as if nothing had happened. The debris shards of iron and neighbors will join the thin, almost metaphoric fog that the universe has become. But for that small while, the void will have a pulse again. The event will have said something simple and important. Even here, even now, change is not outlawed. The timing of these last fireworks is written in uncertainties and quiet extrapolations. How fast does quantum tunneling walk carbon and oxygen toward iron in a crystalline lattice pinned near absolute zero? How heavy must the black dwarf be to find its way across Chandrasekhar's line without the push of accretion? The sums are delicate because the probabilities are so sensitive, exponentials upon exponentials, and because we are projecting known laws into a landscape no instrument will ever visit. Fred Adams and Gregory Laughlin followed those threads and found a number that reads like a lullaby of zeros. Black dwarf supernovas might begin around 1,100 years from now. Others, peering through different assumptions, have placed first flashes as late as 10,320,000 years or beyond. The spread is not a mistake. It is a measure of how small the chances are for each microscopic step and how enormous the ledger of time must be to cache them. Take 10,100 as a lantern to see by a 1 with 1,100 zeros, longer than the universe's current age by about 10,1,090. Even if you shrank all of cosmic history so far to a single Planck time, the smallest meaningful tick in physics, this future would still stand off at a distance that refuses analogy. It is not there to be pictured. It is there to set the mood of forever. The number is not the point. The point is the possibility. Black dwarfs, the cold remnants of suns that fell silent more than 30 years earlier, can still reach a kind of ending that glows. They can do it without heat, without companions, without the dramatic crowded skies of the stelliferous age. They do it by the patience of quantum law, which allows the tiniest of chances to become fate when given ages upon ages to try. And when they do, the cosmos receives its last significant release of energy. These will be the final supernovas, the last punctuation marks in the book of starlight, a proof by existence that changeless is not a state the universe willingly adopts. All the while, expansion continues its soft pull. Structures not bound tightly enough have long since drifted beyond each other's reach. The distances between lonely remnants stretch from light years to millions, then billions, then trillions and beyond. Each black dwarf occupies its own private bubble of space, separated from its neighbors the way islands are separated when the sea rises forever. When one of them explodes, the light leaves at light speed, of course, but the stage itself is expanding. Photons are redshifted as space stretches under them, their wavelengths drawn longer and longer. Across those gulfs, the signal may never touch another object. It may never even cross the relic of a galaxy, because the galaxy is no longer nearby in any useful sense. With time, those photons stretch beyond wavelengths you could fit inside what we would have once called the observable universe. The light becomes part of the background fabric, smeared into lengths too vast to name. There is a tender question tucked in that picture. If an event blossoms without witnesses, no eyes, no instruments, no minds, does it happen in the way we mean when we tell stories? In that late universe, the black dwarf supernovas will be the ultimate unobserved truths. They will make light, neutrinos, and gauzy ripples in space-time, and those signals will travel obediently into an emptiness that offers no receivers. There will be no astronomers to note the curve of the light, no archives to chart the afterglow, no children to ask what it means. The answers go nowhere. The waves pass through everything because there is almost nothing left to pass through. And still, the explosions occur. They are not promises to an audience. They are consequences of laws. Electron degeneracy can hold a star only so long as the star's mass and composition let it. Quantum tunneling will keep flipping rare cards as long as cards exist to flip. Gravity will cash in any imbalance it is given. In that sense, the universe remains gently alive, not lively in the way of bright nebulae and crowded clusters, but faithful to itself. A cold remnant crosses a line and tears. The glow unwraps and fades. The dust drifts on. Nothing in that sequence requires a witness. It is enough that the sequence is possible, and therefore, given enough years, inevitable. You can trace the mechanics with fingertips if you like, because even the hard parts have soft edges. The Chandrasekhar limit is an argument about balance, electron pressure, born from the Pauli rule that identical fermions won't share a quantum chair against gravity's inward pull. The 1.4 solar mass figure is not a cliff with a painted number, but a neighborhood that depends slightly on composition. Still, it is the right neighborhood. Type Ia supernovas are loud because carbon and oxygen, once heated by collapse, burn through runaway fusion and turn the star into a foundry, hurling nickel and cobalt and iron outward in a flash that calibrates distances across the sky. A black dwarf supernova lacks that fuel and that kind of ignition. Its energy comes from gravity's collapse and from nuclear reassembly under catastrophic pressure. That is why its light is 100th to 1,000th of a normal. Type Ia still a beacon, but not a city of light. When such an event ends, the ledger of matter changes. The core that tried to become a neutron star may succeed if enough mass remains and protons and electrons have combined faster than the blowout could stop them. Or the star may disperse too freely, leaving no compact remnant at all, only thin filaments of heavy elements slipping quietly into the already quiet dark. Each outcome depends on details that belong to a physics we can only sketch. How quickly electron capture runs, how the shock forms in a medium that began at nearly absolute zero, how much of the star's binding energy is carried away by neutrinos that do not look back. Whatever the detail, the bright part is short, and the soft aftermath is long. Even this late, the differences of mass and composition matter. Not every black dwarf will reach the line. Some are born too light, ever to trouble Chandrasekhar's balance. They will drift unlit forever, iron never filling enough of the core to tip the scales. Others, larger or with histories that left more of the right mix in the right places, will cross. Those crossings will be spaced not just across space, but across the unimaginable breadth of time. Here, one at 10, 1,100 years, there another at 10, 32,000, and all the lonely dates in between. The universe will mark them not with a calendar, but with isolated waves of light, like stones tossed far apart into an endless, frozen sea. Think of the expansion one more time. If your breath allows it, every unbound structure has drifted away. What remains near anything is what was born near and held fast by its gravity long ago. Even those ties loosen as Hawking evaporation thins black holes and as any residual heat finally vanishes into a background indistinguishable from zero. Against that silence, the photons of a black dwarf supernova leave bravely and thin out, each crest farther apart than the last. Redshift tucks them into wavelengths so long they cannot be trapped or noticed by anything, not because no one is looking, but because looking is a concept the universe has outgrown. None of this is cause for sorrow in the telling. It is simply the long exhale of the same rules that once wove dust into stars. A black dwarf is a promise that time can be stored. A black dwarf supernova is a promise that time can deliver. The last fireworks will not seek the old applause. They will be their own reason final sparks that prove the story does not freeze, even when the stage is made of ice and the seats are empty. The laws don't wait for witnesses. They don't ask for applause or permission. Quantum tunneling will keep its patient whisper. Iron will keep gathering like frost in a quiet well. And among the coldest remnants, some will grow beyond what their own scaffolding can bear. The snap of inevitability doesn't need ears to be real. A wound-up spring lets go whether or not a hand is there to feel it. Yet not every ember is destined to flare. Mass is the quiet judge. Only those remnants that sit close to the Chandrasekhar neighborhood have any hope of tipping into catastrophe. Lighter black dwarfs never get there. No matter how many ages pass, their iron won't add up to the weight that breaks the balance. Our sun is a gentle example. When it exhales its last bright breath, it will leave a white dwarf of about 0.6 solar masses, roughly 60% of what it began with. That sits far below the 1.4 solar mass limit, where electron pressure can no longer stand firm. Even after the ember cools to a black dwarf and tunnels its way, atom by atom, toward an iron heart, it won't cross the line. It will remain a dark, crystal stillness for as long as protons endure. Most endings look like this. Many stars finish as white dwarfs between about 0.5 and 0.9 solar masses. That broad middle is comfortable, solid, and too light to ever collapse from its own gravity. In the great tally of futures, the majority of black dwarfs will simply be converting composition, not destiny, quietly assembling iron that never finds enough company to bring the roof down. Some few sit closer to the edge. Stars that start life in the 6 to 8 solar mass range often leave behind white dwarfs near 1.2 or 1.3 solar masses. Not over the limit, but within sight of it. These are the wall touchers. They cool, they crystallize, and deep within, tunneling promotes carbon and oxygen to neon, magnesium, silicon, and onward, nudging the core toward iron. If enough iron accumulates, if the balance leans just enough, the remnant can approach 1.38 solar masses, close enough that the difference between standing and falling is measured in the disappearance of a few electrons. How many will manage it? The answer hides inside the original distribution of stellar masses and inside the exquisitely sensitive odds of tunneling in a frozen lattice. Current estimates suggest a slim slice, perhaps between 1 and 10% of all black dwarfs could, given ages beyond ages, reach the threshold and fail. A small fraction, yes. But the universe rarely works in small, absolute numbers. Consider only our home galaxy. The Milky Way holds on the order of 200 billion stars. Over the next 100 trillion years or so, the vast majority will end as white dwarfs and later black dwarfs. Even a 1% path to explosion would mean something like 2 billion iron supernovas seeded across what used to be our galaxy's address. And the observable universe? More than 1 trillion galaxies, each with its own sea of stars. Multiply that slim fraction through those vast populations and you arrive at totals around 10, 21, or more numbers that feel less like counting and more like weather. Labels, though, will have washed away. The Milky Way won't be itself. It will have merged with Andromeda and others long before. Then, slowly frayed, some stars ejected to the loneliest orbits. Others surrendered to a central black hole that will itself take an almost unthinkable length of time to fade. Galaxy will be a word without a thing to point at. The explosions will still happen. They'll flicker like rare fireflies, each isolated in its own wide bubble of space, with nobody nearby to answer back. It helps to bring the story close with faces we know. Sirius A, bright winter companion, carries about 2 solar masses. Its farewell, amber, should weigh roughly 1 solar mass sturdy, but well below the limit. No explosion waits for it. It will drift into blackness and stay. Sirius B is already a white dwarf around 1 solar mass. Like our sun's future, it is too light to ever cross Chandrasekhar's line by tunneling alone. Procyon A, about 1.5 solar masses, seems headed for a white dwarf of about 0.6 to 0.7 solar masses. Procyon B already rests near 0.6. These will be quiet stones on the far shore. To hunt for candidates, you look upward in birth weight. Vega, at about 2.1 solar masses, is likely to leave a white dwarf around 0.9 to 1 solar masses closer, but probably still shy. Binary systems can complicate the path. A pair such as Spica, with components of roughly 11 and 7 solar masses, might never make white dwarfs at all if their cores detonate as classic supernovas first. But if the stellar winds and internal details steer them to white dwarf remnants, those remnants could be heavy enough to count among the near-limit few. Here is the knot. We cannot predict the exact final mass with confidence for any given star. How much a star sheds during its swollen red giant breath depends on metallicity, rotation, winds, magnetic tangles, and companion influence. 2 stars that begin alike can end with different cores. What we can say gently is that white dwarfs at or above about 1.2 solar masses carry the right kind of potential. The pathway is long but straightforward once a candidate is chosen by fate. Picture a 1.2 to 1, 3 solar mass white dwarf. It cools for something like 10, 15 to 10, 30 years quickly at first, then with exquisite slowness until it is a black dwarf, its interior a diamond lattice pinned near absolute zero. Over the next ladders of time 10, hundreds, 10, thousands of years, in the exponents rather than the counts, tunneling does its bookkeeping. Carbon fuses, oxygen fuses, neon, magnesium, silicon appear, then conspire onto iron. The core grows more iron-rich and more compact, the total mass inching toward to 1.38 solar masses, a breath from the to 1.4 solar mass threshold we sketch for Chandrasekhar's limit. And then the steps change character. Iron is the resting place. Fusing it won't pay out energy. The tunneling that added mass no longer warms any part of the ledger, but the pressure can still be stolen. At densities high enough, electrons are pressed to such energies that capturing protons inside iron nuclei becomes favorable. Each capture turns a proton and electron into a neutron and a neutrino. The neutrinos flee, almost indifferent to matter. The crucial thing is the vanished electron. Degeneracy pressure depends on how many electrons are there to refuse sharing their quantum seats. Take them away, and the scaffold softens. The remnant sags a little more with each capture, which forces up the density, which encourages more capture. A feedback loop written in quiet. And then the line is crossed. Collapse runs inward like a gasp. The Earth-sized diamond folds toward a core only kilometers across. Gravitational energy pours into the interior, smashing and rebuilding nuclei, forcing shock through matter colder than any winter. What follows is the iron supernova, not blaze like a type Ia, but a severing, The light it throws, perhaps 100th, perhaps 1,000th of a typical Aya, will still be a lighthouse in a night that forgot what lighthouses are. Hours or days of glow, then ash drifting outward, thin and colder than metaphors can bear. Some collapses may run far enough to catch in a neutron star knot before the shock rips the structure apart. Many will unspool completely, leaving only an expanding cloud of iron, a smear of neutrons, a snow of other nuclei. If protons decay, time will thin even those remnants to nothing in their own great span. If protons do not, those lonely atoms will wander, separate by distances so broad that encounter becomes a word without use. Even within this quiet, the numbers keep their gentle place. The Chandrasekhar threshold remains roughly 1.4 solar masses. The sun's final ember stays near 0.6. The everyday range for white dwarfs, 0.5 to 0.9, describes most outcomes, with the rare heavy cores of 1.2 to 1.3 solar masses standing near the tipping post. A guess of 1 to 10% for eventual iron supernovas feels small until you echo it through 200 billion stars here and 1 trillion galaxies there. Multiply, and you get a sky that will, over unimaginable durations, host countless last sparks, perhaps around 10, 21 of them each, too far from the next to trade even a rumor. The distances between these black dwarfs grow while we wait. Expansion keeps its slow pull. Unbound structures move apart until near loses meaning. When an iron supernova goes off, its photons sprint outward at light speed, but the stage itself stretches beneath them. Wavelengths lengthen with the redshift, crests pulled apart like threads teased from a cloth. Most of that light will never brush another remnant. Most will never be gathered by anything at all. It will simply join the silence, the way wind will sometimes lift snow into brief silver and set it down again without a footprint. None of this requires an observer. That is the strange comfort woven through the far future. Events do not need eyes to earn their happening. Quantum tunneling doesn't check for company. Electron capture takes no roll call. Gravity answers only to the mass in the room. So the universe, wound like a spring by its own rules, releases that stored tension where and when those rules say it must. Explosions bloom, however faint, because the equations still add up to yes. Some remnants will never know that turn. Lighter black dwarfs will stay as they are, iron inside, diamond throughout, electron scaffolding intact, unmoving and unremarked upon. Heavier ones, if they began close enough and tunneled far enough, will cross the point where electrons cannot stand the weight. In each case, the ending is perfectly ordinary for that remnant. It is only from our warm age, filled with color and breath, that the tale feels surreal. A universe that grew dark long ago, still finding a way to wink. Think of Sirius A again, headed toward a 1 solar mass ember. Sirius B, near the same. Procyon A, dropping to about 0.6, 0.7. Procyon B, already resting at to 0.6. Vega, likely around 0.91. All too light to trouble the limit on their own. Think of rarer descendants of heavier stars if winds, spins, and metallicities conspire, coming to rest at 1.2 or 1.3. Their fates are the ones that keep a door open. We cannot tag them now, cannot circle names. The precise end mass is the sum of details too fine for forecasts across such stretches. But we know what to look for: closeness to the threshold, patience measured in ladders of zeros, and a lattice that lets chance try again and again until chance becomes certainty. When one of those certainties arrives, the scene will be the same as all the others. A small region of space suddenly lit, neutrinos streaming through everything, a murmur in space-time, then dimness, debris expanding into distance. If proton decay is true, the pieces will eventually unmake themselves. If not, they will persist as iron and friends, so thinly spread that interaction is a story they will never tell. The universe will return to what has become its default, dark, cold, and content to be so. It is tempting to call this sad, but the feeling that follows is quieter than sorrow. It is the sense of a promise kept. Physics said what would happen when mass met pressure under these conditions. It said what tunneling would do given time. It drew a line in the sand for electrons and dared gravity to push. The universe waited long enough to see whether those sentences were true. They were. A black dwarf found the border of its support, and the last fireworks rose, not to be seen, but to be. The little patch of space that flashed awake settles again, as if a match were struck in a winter field and then cupped out. What remains is what was there before, cold, so close to perfect, darkness, so even that direction loses its meaning. The light had a beginning and an end. It traced a brief arc and then let go. That arc still matters. It changed the bookkeeping, turned bound mass into flying ash, sent photons and neutrinos on their solitary journeys, and then gave the night back to itself. What follows after the last of those rare flares is the endgame's end. Nothing substantial is left that can release fresh stores of energy. All the clocks that could ring have rung. The universe comes to what cosmologists, in their careful way, call true heat death, a final balance where gradients have flattened and no further work can be coaxed from the stage. Not an explosion, not a curtain fall, just a room that has relaxed into stillness so complete that change becomes a rumor. Imagine the inventory, assuming protons endure. There are black dwarfs that never crossed the threshold, and others that did and left only thin debris behind. There are neutron stars here and there, stubborn knots of matter held by a different kind of quantum scaffold. There are black holes, quiet, massive, unreflective, waiting out their own long physics. Between these, a diluted mist of particles drifts, photons softened by redshift, neutrinos inattentive to matter, electrons, and possibly positrons whispering past. Everything is cold, everywhere. The distance between atoms, when atoms even appear, is so large that you could cross for trillions of light years and never brush one with your sleeve. The last notable actors are the black holes. They do not flare by chemistry or by collapse. They fade by a quantum effect traced at their very edges. Hawking radiation is thermal, and its temperature falls as a black hole's mass rises. Big holes are colder than small ones. A solar mass black hole would glow at roughly 60 nanokelvin, about 60 billionths of a degree above absolute zero. A supermassive black hole, the kind that once anchored a galaxy's center, would be colder still, perhaps a trillionth of a degree or less above the floor. Today, such temperatures are nowhere near the 2.7 Kelvin wash of the cosmic microwave background, so holes gain more from the sea than they lose, but the background is not fixed. Expansion stretches its light thinner and cooler. Far ahead, on the order of 10, 20 years or so, the background dips below the temperature of even the largest holes. Net loss begins. The long unspooling gets underway. Evaporation, is patient at first. The rate at which a black hole radiates is inversely tied to its mass, so the more it weighs, the slower it leaks. A hole with the mass of our Sun would need around 1067 years to finish. Scale up to 1,000,000 suns, and you're in the neighborhood of 1085 years. 1,000,000,000 suns, 1098 years. These spans make the black dwarf fireworks feel like quick glances. The late universe becomes a place where black holes are the only objects doing anything thermodynamically interesting, very slowly turning mass into radiation, adding occasional quanta to the thinnest sea. As mass drifts away, the process accelerates. Smaller means hotter. Hotter means more radiation. More radiation means smaller still. A runaway gathers, not explosive at first, but ever less subtle. At the end, there is a flicker that concentrates the last of the energy into high-frequency light and particles. By the arithmetic of Einstein's old sentence, the total energy is just mass times the speed of light squared. For a solar mass hole, about 1047 joules. That is an ocean beyond our ordinary comparisons, more than the Sun will release in its luminous lifetime by many orders of magnitude, and yet spread across 1067 years. The average trickle is less than the warmth of a living body. It is brightness in slow motion. The final flash, though real, is tiny beside a supernova, and tinier still beside the human metaphors we borrow for spectacle. When even the last black hole lets go, the stage is left to low-energy particles and nearly weightless light. If protons decay, then in a separate ledger of ages, their remnants have already unraveled into leptons and photons. If protons are permanent, then protons and neutrons linger as the rarest furniture, drifting so far apart that interaction becomes an antique word. Expansion keeps pulling. Density thins. Temperature presses itself against the quantum limit of cold. No gradients worth naming remain. No engine has a door to open. This is what the phrase maximum entropy tries to hold. Not ruin, exactly, but the condition in which there is nothing left to rearrange for gain. And yet the mind does not sit comfortably with a horizon labeled "nothing happens." Some physicists have asked the question that threads its way through this room. Even here, could fluctuations stir? Quantum fields never stop trembling entirely. The vacuum is not an absolute emptiness, but a set of rules with a baseline itch. In principle, on some absurdly long timescales, a random bump could throw together a handful of particles, or a cluster of them, or push the math far enough, a structure more elaborate. Stretch the idea until it squeaks, and you arrive at the thought experiment called a Boltzmann brain, a self-aware pattern conjured by chance out of the vacuum, complete with false memories and a sense that it has always been alive. The probabilities are so small that the numbers hide behind stacked exponents, things like 10, 50 years, as a typical weight. A 10 raised to a power that itself needs 50 digits to write. The mind refuses. This not on sentiment, but on scale. We can say only that if the future is long enough and the universe large enough, even humiliatingly small chances cash out somewhere. Whether the vacuum has the right properties, whether consciousness is meaningfully possible in such a ghostly form, whether time itself has a physical meaning in a world without clocks, these are questions at the border where physics shades into philosophy. There is another line of speculation that keeps a candle in the window. Quantum mechanics allows more than particles to tunnel. In some models, even the vacuum can jump from one state to another. A transition like that could spawn a separate expanding region, a bubble, where the rules particle masses, coupling strengths, perhaps even dimensions, differ from ours. Such a baby universe would peel away and grow on its own terms, with its own arrow of time and its own story of heat and cold. If such budding happens, then heat death is not an absolute end, merely the local weather in our patch of the multiverse. The rest proceeds elsewhere, beyond any horizon we could ever cross. It is an idea born from taking our current equations into places they were not designed to go. The math can be elegant. The evidence is none. Still, it is one more way the narrative refuses a hard period. In the near-perfect quiet that remains to our region, the meaning of near vanishes. Space stretches, but stretching does not change the feeling when nothing in it answers back. A photon sent from what used to be a black hole's last sigh will lengthen and lengthen until its crest-to-crest distance exceeds what any language would call a wavelength. Neutrinos will glide, not so much lost as unnecessary. Electrons will wander alone for distances that no metaphor measures. If protons are stable, a chilly census would still find them somewhere, but so scattered that two of them passing within a light year becomes a calendar event the universe never notes. The black dwarfs that never cross the line remain, their cores iron and their lattices perfect. No warmth, no pressure to negotiate, no rails left to run. They do not erode. There is nothing to erode them with. If proton decay is part of nature's longer script, they will thin out by rare clicks, losing their substance in intervals that make all other intervals feel like songs. If not, they will persist as stones in a garden no one walks. Neutron stars that escape capture by black holes keep their dignity. Neutrons locked by degeneracy. Magnetic fields, a fossil that has no wire to thread. They, too, radiate their last and settle into being. The calendar words lose traction, but a coordinate labeled time still ticks in the equations. Whether that tick deserves to be called time is its own argument. If nothing changes and no clock measures it, is passage real or only a parameter? The safest thing to say, in a whisper that respects both science and silence, is that the laws continue to hold form. They do not vanish for lack of audience. If a fluctuation is permitted, it will sometimes happen. If a tunneling path exists, it will be stepped along given enough chances. If no path exists, there will be nothing, and that nothing will be complete in its way. Return, for a breath, to the long staircase that brought us here. Stars formed, burned, and rested. White dwarfs cooled into crystals. Quantum patience turned carbon and oxygen toward iron, and a few of those iron hearts crossed a limit and failed, sending the last bursts of light into distances that did not care. Black holes, slower than slow, turned mass into radiation and then into memory. The leftover field is smooth now. Work is finished. The universe did not end with a crash. It exhaled until the exhale could not be felt. There is a tenderness in that picture, if you let it in. We like to think of endings as events, but most endings are conditions. Heat death is not a door slamming. It is the absence of any new doors to open. Our laws, stern as they may sound, are not cruel. They simply do what they always do, at whatever scale and pace the circumstances provide. Once, they shaped pillars of gas into stars and set the breath of fusion inside them. Later, the same laws held electrons in their seats and let the cold press matter into diamond. Later still, They allowed tunneling to keep its tiny promises until an iron heart crossed a line. Even later, they let horizons glow away the mass that sat behind them. At the last, they keep the vacuum honest and the fields humming at their floor. Somewhere within that floor, someone has imagined a fluctuation writes a mind into being for a moment, and the mind looks around and remembers a childhood that never happened. Somewhere else, if the vacuum can tunnel the first light of another cosmos snaps on inside a bubble and a new list of constants begins its march. Or perhaps not. Perhaps no such exceptions exist, and the right answer is the simplest one. The room goes very still and remains so. Either way, the story we have followed keeps its shape. A black dwarf's brief bloom leaves its tiny scar. The region cools, the ash drifts, the quiet returns. Black holes keep their long appointment with evaporation. The last sources of energy go silent. What remains is a universe so even, so fully rested, that there is nothing left to rearrange. If that feels austere, set it beside the gentleness of inevitability. The laws of physics did not tire. They did not forget us or anyone. They carried on until there was nothing left for them to change, and then they continued to be true, which is another kind of change, the change from becoming to being. You can let your shoulders fall here. The picture is large, and it does not ask to be held tightly. Light had its time, and so did warmth and motion and the quiet fireworks at the end. What remains is not a sadness, but an absolute, like a lake finally frozen smooth after a very long winter night. In that smoothness, meaning does not vanish, it rests. And the universe, having told every story it could tell with the tools it had, lies back into its own calm, with nothing left undone. It's a simple, almost audacious habit to take the laws we know, carry them far out across the map, and listen for what the mathematics murmurs back. Sometimes it says, nothing of note will happen. Sometimes it opens a very strange door. Black dwarf supernovas belong to that second door, a delicate but stubborn possibility, where quantum rules gather countless tiny no's, stack them across ladders of nearly endless time, and eventually turn them into a quiet, inevitable yes. From here, a soft philosophical current slips in. These explosions whisper that the universe, no matter how old or how still it seems, never truly freezes. Even 10, 1,000, 100 years from this breath, a number long as the dark events can still arrive, change does not stop. It only shifts into a rhythm our minds rarely imagine. That sense brushes against our idea of time. If someone insists that time is another name for change, then even in regions that look utterly motionless, a small motion persists, sustained by quantum tunneling. The river never halts completely. Somewhere, the nearly impossible keeps happening, like a slow pulse in the distance. This makes the questions around determinism and the arrow of time feel gentler, too. At the particle scale, the equations don't choose a favorite direction. Run a collision backward on film, and it still looks allowed. But when many particles crowd the stage and thermodynamics begins to speak, order slides toward disorder, entropy climbs, and time grows a direction. Black dwarf supernovas keep step with that arrow. They are the final sigh of free energy that once pooled from the earliest fire. The young universe began in a low entropy state, dense with energy and structure. Across 13.8 billion years, that energy slowly spread. Stars formed and died, black holes gathered and evaporated, and disorder increased. These late iron-born flashes are the last punctuation of that sentence, the final spill of energy before the page becomes as even as it can be. Yet beneath the physics, a quiet beauty shows through, as if the universe remembers. An iron core in a black dwarf doesn't appear from nowhere. It's pieced together by tiny tunneling steps carried out over 10 hundreds or 10,000s of years. Each step is individually all but impossible. Together, they become something that cannot be avoided. When the remnant crosses the Chandrasekhar threshold and fails, the event isn't random. It is a closing phrase written long before. From the moment the original star kindled hydrogen, through the swelling red giant years, into the cooling of a white dwarf, and then the long dimming toward a black dwarf, until electron capture unthreads the last support. One stitch runs through time and leaves its final knot in a distance so great that stellar lifetimes look like blinks. In that way, each far future blast feels like a postcard mailed from the distant past. The star that set this in motion died more than 30 years ago. Any civilization that once watched it is gone. Even the galaxy that cradled it has thinned into memory. But the same physics that taught us how stars form and how they fade keeps its promise. In the end, those laws still hold enough to lift one more light, proof that nature's rules persist when every backdrop has vanished. There's a tender sense of fairness here. Stars too small to explode when young like our sun are given a theoretical second chance. Our sun will never claim the drama of a supernova. It's too light. When it dies, it will shed its outer layers and leave a cooling white dwarf. No spectacle, only a patient fade. Yet, in principle, if its remnant could somehow collect enough extra mass, say, by merging with another white dwarf, it might one day explode as a black dwarf. Not by quantum tunneling alone, since that remnant is too light for that path, but by some other exceptional mechanism we have not considered. The odds are vanishingly small. In a universe of widening distances, white dwarfs are far too scattered to merge in any realistic future. Still, it is sweet that the equations allow the door, even if nature almost never walks through it. In practice, the true candidates are the children of heavier stars, white dwarfs above about 1.2 solar masses. Their parents burned bright and hot, fusing up to carbon and oxygen or beyond, living for millions or billions of years rather than the slow trillions granted to the smallest suns. They left behind heavy cores. These heavier white dwarfs cool like the rest, but carry the potential for a final act. Through tunneling, they build iron, and in the far reaches of time, cross the Chandrasekhar margin and explode. They get to be supernovas, after all, just delayed by 100 years or so. Imagine, if it were possible, what witnessing such an event would be. You float inside a universe that is not merely dark, but empty of light sources. No stars shine, no galaxies ribbon the distance. The microwave background has cooled to an almost perfect stillness. Space is black, not the black of shadow, but the black that arises when there is nothing left to glow. Then a point appears. By the standards of today, it is faint, perhaps 100th or 1000th the luminosity of a typical type Ia supernova. In absolute night, it is blazing. It is the only thing visible in any direction. Its light is pulled red, stretched by the expansion that never stopped. A spectrograph, if you had one, would whisper of iron and heavy elements, smeared and dim. You could read the story. An iron-rich object exceeded its stability and tore itself open. Days, maybe weeks, and then the ember fades. Night returns, clean and complete. You might wait billions of years longer for the next such spark, and it would likely blossom far away and far elsewhere, so far that how far loses meaning. Of course, no mind will see it. Consciousness, whether chemical or crafted, needs gradients, scaffolds, and fuel. Here at the end, only the brief flare of the explosion offers a gradient, and it is over too quickly to build anything upon. All witnesses are metaphors. What remains is a chain of consequence. Tunneling does its work. Electron pressure is eaten by capture. Gravity wins, and the blast writes the final comma in the story of light. When we speak of meaning, we return to time. Time doesn't need a conductor to move. It needs a difference, and difference remains rare and short because of quantum rules. Beyond that, even when everything finally drifts toward level, some people ask, is level truly absolute? There are meditations on vacuum, tremors, random fluctuations that might birth a handful of particles, or in a wilder sketch, something more intricate. In the folklore of physics, this becomes the Boltzmann brain, a consciousness thrown together by chance, complete with memories no history ever made. The probabilities are so small that exponents must be stacked on exponents times like 10, 50 years, notations that exist only to remind us we've stepped past what can be pictured. Does this vacuum have the right properties? Can consciousness mean anything in such a ghostly architecture? Is time still the right word when no clocks can tick? Those are questions that stand on the border between physics and philosophy. There's another faint line sketched across that border. Perhaps the vacuum itself can tunnel, jumping to a new state and opening a bubble with fresh rules. Such a newborn region would expand on its own terms, with its own constants and its own tale of heat and cold, while our patch remains still. There is no evidence for it, but the mathematics does not forbid it. It allows the possibility that a bud might split from an old trunk. Whether or not that happens, nothing disturbs the core of our picture. In our small province, the universe keeps its gentle vow. Follow the seam one more time with your fingertips. A modest star quivers to life, stitches hydrogen into helium, swells red, and lets its outer shell drift into a lantern of gas. Its heart contracts into a white dwarf, shining not because it burns, but because it remembers being hot. Over ages beyond names, it cools. Inside, carbon and oxygen crystallize into a planet-sized diamond. Then, tunneling small, patient walks carbon to carbon, oxygen to oxygen, onward to neon, magnesium, and silicon, eventually settling into iron. When the remnant is heavy enough, electrons are captured, the quantum scaffold thins, and gravity drops the ceiling. A softer, dimmer detonation arrives. A sweep of light crosses emptiness, ebbs, and the emptiness takes back its shape. It feels like a very slow piece of music, beginning in the bright chord of the Big Bang, passing through the middle movements of stars and galaxies, leaning into the low notes of black holes, and closing with the single, spare tones of black dwarf supernovas. The arrow of time does not turn. Entropy keeps its road, and at the end, when all the steps are leveled, the story of light closes with the smallest possible period. Even that period carries a message. The laws do not need an audience to stay true. They are patient as breath, steady as stone, gentle as night, a set of lines written once for all time. If there is a sense of rightness here, it comes from how remnants finish according to their nature. Heavier ones, the children of bright, short lives, are allowed one final line. They burned up to carbon and oxygen and left large cores. They cooled like everyone else, but close enough to the limit that a handful more iron syllables in the ledger brings the collapse. Most others, light as our sun's progeny, remain frozen and spare, snowflakes that never melt. The universe isn't playing favorites, it is recognizing mass and opportunity. The light, stay in quiet, the heavy touch flame once more. Call that meaning, if you like the meaning of a well-edited book in which each character ends in the way the opening promised. Or call it comfort. Even when light fades, the foundation that once lifted it remains unchanged and unwearied. That is why the tale can stretch to 10, 1,000, 100 years without unraveled threads. That is why we can trust that a late spark, however delayed, is part of the larger order, not because it's seen, but because it is permitted. In a room this still, you can let the shoulders ease and breathe. Imagination can wander far and return unhurried. There are no announcements, no stagehands moving scenery, only a seamless flow. The universe has shown, in example after example, that it prefers endings that are clean. A black dwarf flares, grows dim, and rests. A black hole drips light until there's none left to give. A vacuum keeps its subtle habits. This is not the last stanza of a song. It is a long, fading note, held until silence is complete, long enough for every echo to unspool and vanish. And in that quiet, if you lean close, you still hear the earliest truth physics ever whispered. There are gentle laws, and they are enough to tell the whole story. They flare for a breath, and then are gone, too brief, too solitary to cradle anything like life or mind. The light rushes outward across emptiness, a spray of photons with nowhere to land, no dust to warm, no leaf or lens to meet. They pass through a universe that has set down its tools. The explosions do not arrive because the cosmos needs them or because some purpose is waiting. They arrive because the laws, left alone with enough time, do what they must. That, perhaps, is the deepest note in this whole tale. The universe runs on mathematics that keeps working whether or not the results are beautiful, whether or not anyone is there to notice. The equations do not ask for witnesses. They simply trace what follows when you give them certain beginnings and let the clock drift forward. A black dwarf supernova is not a special quest the cosmos undertakes. It is the plain consequence of quantum mechanics and gravity laid over the husk of a star for longer than language can hold. The Pauli exclusion principle quietly keeps electrons from sharing the same seat. The Heisenberg uncertainty principle leaves no particle with a perfectly known pose. The strong and weak forces knit and unknit nuclei. Mass bows space-time, and space-time answers back. Fold those into a single room. Dim the lights to almost absolute zero, and wait on the order of 10, 1,000, 100 years. The outcome is not planned, but it is permitted, and once it is permitted for long enough, it becomes natural. There is a delicate lesson about law itself tucked there. Physical laws are not edicts that command events. They are boundaries that sketch what is possible. They do not write the date and address of a future supernova. They say, instead, if such and such conditions are met, and if the world is given time, then this outcome lives within the fence. A cosmos as broad and patient as ours wanders its own possibility space. overstretches that dwarf imagination. It samples path after path. Among those, black dwarf supernovas are simply some of the turns it will eventually take. From that sampling rises a set of questions with soft edges. If time is effectively unbounded, do all allowed events eventually occur? Does probability thin out into inevitability when the waiting never ends? The answers may live beyond our reach because they require pushing known rules into a country where new rules might awaken. It is not even guaranteed that the constants themselves, the strengths of forces, the masses of the small will remain as they are. If those drift over the longest scales, then the tunneling rates change. Chandrasekhar's neighborhood shifts, and the whole dance might end differently. For now, every careful measurement whispers that the constants are stubborn, fixed within our sightlines, as far as our instruments can tell. Hold that steady, and the far future fireworks remain on the table, unless something even more fundamental steps in first. That something is the question of the proton's patience. Grand unified theories often predict that protons do not last forever. Experiments have only managed to set a lower bound around 1034 years. If the real lifetime lands around 1036 years, or any span comfortably smaller than to 1,100 then protons, and with them neutrons in ordinary matter, will have unraveled long before a black dwarf can tunnel itself into an iron heart heavy enough to fail. In that storyline, no iron supernovas blossom at the end. The remnants dissolve grain by grain. Matter loosens into leptons in light. The universe glides from a white dwarf, black dwarf age into a thin radiance without pausing for a last set of sparks. If, on the other hand, protons are stable or so long-lived that their timer runs longer than 1,100 years, then black dwarfs take their turn as the true final act. They are the last meaningful release of energy the cosmos can muster. After them, there is nothing left to light, nothing left to push or pour or warm in any lasting way. Equilibrium isn't an event, it is a condition, and at last the condition is complete. Strange, then, that the two roads, protons that die too soon for the fireworks, or protons that live long enough to permit them, end in almost the same view. Either way, a cold, dark quiet spreads in all directions. Particles grow lonely. Distances stop being measured in familiar words. The map loses its landmarks. By the habits of our nervous system, that picture reads as bleak. We were shaped in pockets of contrast, and we crave edges. Day against night, warm against cold, signal against noise. A universe that smooths itself, this thoroughly feels like the absence not just of life, but of meaning. Yet the universe is not a storyteller with a taste to satisfy. It is a set of laws applied to a set of beginnings. One of those beginnings led to the stelliferous era, where stars learned to write and planets learned to listen. Another led further on to a long winter of evenness. The math isn't unkind, it is merely faithful. What that means for us depends less on physics than on the philosophies we carry. If meaning is something the world must provide from the outside, then heat death looks like a verdict. If it is something living minds can create, share, and pass hand to hand, then meaning is local and real wherever it is made, and it needs no permission from far future ice. It is remarkable, after all, that any of this was possible, that the constants sit where they do, that gravity is weak enough to build spaciousness, and strong enough to gather stars. That chemistry can lace complexity. That awareness can rise and ask. We are outrageously fortunate to stand in the warm middle, the stelliferous interval, where the universe is crowded with interesting things. The very idea of a black dwarf supernova is a reminder, even when everything appears over, physics keeps breathing. The universe does not end, it changes state. And every change of state, no matter how slow or how cold, is still an act in the same play, governed by the same lines. There is a comfort in that, not a soft blanket, perhaps, but a steady floor. The cosmos doesn't wind down and stop like a toy, forgotten on the shelf. It keeps finding lawful ways to become different, even after the obvious engines have burnt out. Quantum mechanics guarantees a sliver of possibility for almost everything, a non-zero chance that a system will land in a neighboring posture if given enough attempts. That applies wide and deep, to the slow edits inside a black dwarf, to the long unraveling of black holes by Hawking radiation, perhaps to the vacuum itself, which might one day tunnel into a different state and bud a region with new rules. The universe we see is a single frame from a film that runs in both directions, back past the earliest light, forward beyond any sentence we can write. We know only a short clip. The reel is longer. So those last explosions, unobserved and unnecessary by any ordinary standard, carry a small truth large enough to fill the sky. The laws are indifferent, but enduring. They do not promise us drama. They do not apologize for quiet. They hold steady whether the outcome is a nebula, a living ocean, a diamond planet, or a night whose only spark is a single iron heart giving way. In that steadiness lives the possibility that everything changes given enough time, including the conviction that nothing will. The odds may be microscopic, the weights obscene, the stages empty. Nevertheless, what can happen, happens, somewhere, sometime. It helps to think of law not as a script, but as a boundary. Within the fence, the world can wander. In an effectively infinite track of time, the world will wander a lot. We are glimpsing from a bright middle chapter, a page far ahead where the wandering is slow and spare. That page may include proton decay that washes the ink away before any last punctuation is set. Or it may allow the ink to dry into iron and crack open at the very end. Either page ends in the same binding, a smoothness that refuses further work. The vision is austere, but it leaves our present strangely richer. We are here, and here means a balcony in cosmic history, with a view of both blaze and hush. We can recognize the stelliferous era as brief and extravagant, and love it more for that brevity. We can laugh at our luck without wasting it. We can build meanings that do not need permission from a far rustle of numbers. And when we look forward, we can accept that the future will not be shaped around our appetites, but around the quiet commitments the laws have made since the first instant. Black dwarf supernovas are one of those commitments kept on a schedule that dwarfs calendars. They will occur unobserved. They will throw photons into a room with no walls. They will obey, not inspire. Yet they will stitch one last sentence into the fabric. Not the end, but still true. After that, the story thins to a smoothness that lets nothing else be written upon it easily. If protons decay early, the page is cleared sooner. If they do not, a few small sparks dot the margin and fade. Either way, the book remains, and the grammar that made it remains with it unmoved by the presence or absence of readers. Perhaps that is the quiet blessing of this late chapter, to know that the same rules that wrote sunrise into oceans and breath into lungs are the rules that, at the far edge, will write a final, lawful glow into a place without eyes. They are not tender or cruel. They are constant. And in their constancy, even the end of obvious things becomes a kind of continuation, not life everlasting, but law everlasting, not meaning decreed, but meaning made while the lights are on. We are part of that making. The universe does not promise we will be around to see how the last commas land. It promises only that commas will land where they must. For now, we are here to watch, to learn the pattern, to feel the warmth while it lasts, and to rest in the knowledge that even the quietest future remains a future, because the laws will keep speaking softly until there is nothing left for them to say. We happen to be living in a passing phrase of a much longer sentence. The process goes on whether we are here to notice or not. Black dwarf supernovas are reminders of that bigger cadence. We are temporary. The unfolding is not. They point to timescales that sit far beyond the reach of human intuition and show that physical processes keep working across them. Observed or unobserved, they are the ultimate long-term consequence of stellar evolution, the last act in the story of how matter behaves when gravity and quantum rules share the same stage. They also nudge our intuitions about endings. We tend to imagine a final state as a place where the story stops. Physics suggests there are no stops, only thresholds. Every arrangement of matter and energy carries a non-zero chance of becoming some neighboring arrangement. If the clock is allowed to run long enough, even tiny probabilities eventually take their turn. So the universe does not end so much as it moves through a sequence of conditions. The age of stars gives way to the age of remnants. The age of remnants gives way to the age of horizons. The age of horizons thins into the age of dark, and even that may be a vestibule for something we do not yet know how to name. Black dwarf supernovas are an emphatic mark at the edge of one such transition, small fireworks before a longer quiet, and proof that the cosmos keeps a few late moves in reserve. We will not be present for any of it. Humanity will be gone long before the first white dwarfs have cooled enough to begin the patient tunneling that builds iron, one unlikely step at a time. The sun will finish its bright work. Earth will be lost. Whatever we leave behind will fade into background hush long before the earliest candidates prepare their final collapse. The gulf between our hour and those events is so enormous that language feels thin trying to span it. And yet, we can imagine. Mathematics and physics let us follow the logic. How stars exhaust their fuel, how white dwarfs harden into planetary diamonds, how quantum tunneling slowly edits nuclei toward iron, how electron capture steals the pressure that holds everything up, and how, in that failure, the last light is made. Imagination is not the same as observation, but this, too, is a way of knowing. It ties our small lives to the deep rhythms of the cosmos, rhythms that run on scales billions of trillions of times longer than a human lifetime. Look backward for a moment to see how far forward we've learned to look. From a hot, dense beginning, about 13.8 billion years ago, the universe expanded and cooled. Atoms formed, stars lit, galaxies assembled, planets gathered. Life emerged at least once and learned to wonder. Now, after those 13.8 billion years, some of that life has enough perspective to sketch not only a beginning, but also a far end, and not with prophecy, but with equations. We can project the fading of stars, the cooling of embers into black dwarfs, the slow ascent to iron, the crossing of stability, and the last glimmer that follows. We cannot watch these things unfold, but we can recognize that they belong to the same rules that bring day and tide and chemistry and breath. That recognition is remarkable on its own. It is also a test. The idea of black dwarf supernovas stretches everything we know across 1,100 orders of magnitude in time. It leans on quantum effects whose odds are almost zero in any ordinary era but become inevitable given long patience. It stands where general relativity, quantum mechanics, thermodynamics, and cosmology overlap and strain, and still, we can talk about it in complete sentences. We can estimate when the first of these events might occur, how bright they might be, what they might leave behind. We cannot touch them, but we can reach them with reason. That reach, fragile, provisional, always open to correction, is a quiet triumph of how our minds work when they are at their best. So here we stand, 13.8 billion years after a beginning, trying to see across a span so wide that our entire history so far is less than a blink against it, and naming from here the last lights that will ever shine. Black dwarfs do not exist yet. They will not exist for quadrillions of years. They will not explode for stretches incomprehensibly longer than that. But the logic is steady. They will exist. Some will explode. When they do, they will show one final time that age and stillness do not amount to absolute. Stop, that even at the edge of everything familiar, something can still happen. Those explosions will be faint and brief and alone. No record will be kept. No memory will hold them. They will occur without audience or purpose because the laws allow them and because the conditions for them have finally ripened. There is an austere beauty in that. A last, clean demonstration that natural law remains itself without the need for anyone to witness it. Time will go on. A remnant somewhere will step past its support. A point of light will appear, then dim, and the page will smooth out again. But the page will not be quite what it was. One more black dwarf will have finished its long sentence. One more consequence, seeded when a star first kindled, will have come due. One more line will have been added to the ledger that began when the first atoms cooled enough to bond. The change is small against the size of the book, but it is real. It says, the rules held all the way down. And that is a fitting place to leave the thought. We inhabit an interval in which the universe is lively, complicated, and generous with contrast. We are unlikely and brief within it, yet we can understand enough to trace how a story like this could possibly end. Black dwarf supernovas remind us that endings in physics are not hard walls. They are limits that are approached, crossed, and then replaced by new limits. The Stelliferous era gives way to another, and then another, and then another still, each one less dramatic than the last, but each one faithful to the same grammar. The very last punctuation marks, if protons are stable long enough, will be modest and scarce, tossed like sparks across a landscape too wide for echoes. We will not be there to see them, and that does not matter. What matters is that we can follow the sentence to its edge, hear what the laws are saying, and know that the story's quietness at the end is not emptiness, but completion. In that completeness, there is room for gratitude, not to the universe, which neither asks nor answers, but to the tiny span in which we found ourselves able to learn. We learned enough to say how stars live and fade, enough to see why the last embers might flare, enough to accept that the future will not bend to our sense of drama, and still care to understand it. That is more than most atoms ever get. It is enough. Somewhere, far ahead, a remnant will exceed its balance and break. For a while, something new will happen. Then the ledger will quiet again, and the long arithmetic will carry on in whatever form remains. The rest belongs to time.